Just to give you an idea that we don't really have to have hugely dense broadcast domains. Okay, here it's with 7, there it's with 35. You might say, oh, that's quite a lot, but this I think is very, very reasonable. The other way, I'm not going to show you the other ones. I think max is probably obvious. Or you can, if you compute mean, you can just negate all bits before doing the arbitration and have max. We can also do what we call the interpolation of sensor data. I'm going to try to go through this quickly. So, what is this that we call getting the interpolation of sensor data? Say that you have a signal that changes in time and space. This is our idealized signal. It's this kind of shape. And let's assume that we have deployed lots and lots of sensor nodes. So we can measure very, very, very closely this signal, okay? We can almost imagine that you have a sensor node for each x and y coordinates, okay? I know this is a bit too much, but imagine that you have almost for each x and y, you have a sensor that can measure this shape. Okay. So how can we get this signal? How can we have an idea of this from our sensor nodes, get the readings, and look at this signal? Okay. So obviously, what we can do is to get all sensor values and build this shape. Okay, that's easy enough. But imagine that this signal changes in time, and it changes rather quickly. Okay. So we would have to get all the sensor data, gather this shape of the signal, but then we would have to do it again because the signal has changed, and we would have to be able to do this fast. So, say a few times per second. So, you're probably getting all the sensor values is not a good idea because that will probably take a lot of time, and it will depend on how many sensors you have deployed there. So, what we can do is, instead of getting the whole data, just try to get some points, okay? Imagine we get this point here, this point here, this point here, and this point here, and then from those points, we try to figure out what is more or less the shape of our signal. Instead of getting all the data, we just get a few points and try to interpolate the rest of the signal. Obviously, this needs some assumptions about how the signal changes. So one way we could do is just select nodes at random. Why not? But the thing is, if we select nodes at random, we selected just 1, 2, 3, 4, 5, 6 nodes here. Those are like where we have these bars. It's where we selected the points, and then we've done an interpolation, a weighted average interpolation, and we get that. It's not a very good match with our original signal, right? So, but can we actually get with these only 6 points, can we actually get a good idea of that signal? We actually can. If we had chosen these points, then I guess we can agree that it is a good fit with that one. Our interpolation would give us a rather good idea of how our signal is. So, can we select those nodes? Well, the thing is, the way we can select those nodes, it's by doing this. Just iteratively select the node with the highest error, and we start with a flat surface. So I'm going to just iterate and show you how those points are selected. So we start with a flat surface, and we pick the node that has the highest error to this flat surface. So what is the node with the highest error to this flat surface? It's the node that has the sensor reading on the top of our signal. You see our signal had that shape, so it's the node on the top. Then we select the next node that has the biggest error related to this, how it is now, the current state. And that is a node on one of the corners, right? Because it's from the top, and the biggest difference is down here, okay? And then we have all these, right? Because all these also have a big difference, because the reading of the sensors is down here, and our interpolation is here, so this is the biggest error. So iteratively, we are selecting them, and we end up with this. And then we can select one more to be basically the same. So how can we select those nodes quickly? That's easy. We can use YDOM to get the node with the highest error. We just do a tournament, and the node with the highest error will win the tournament. And that makes you have those points very quickly. Is that? So, related to the algorithms to exploit YDOM, so this second part of the talk, we have shown this, how we can compute max and do an interpolation. Okay, we have also done. We have also shown. I didn't put here. I'm sorry. How to estimate the number of nodes or live nodes, or the number of nodes that can and that have a certain property, for example. And we also developed. We also thought about, and we have some results about it, how we can use this in an environment with multiple broadcast domains, okay? Because in general we would like to do it. And I have a slide just to talk about a little briefly about more results about this and this. So in practice, the other thing that I have about computing min and max and interpolation in single broadcast domains is just showing you this, is showing you that we have implemented this in those new platforms, and those new platforms enabled this to be competitive, okay, to be fast enough so that we can actually say that it is practical and it has advantage over doing it in some other way. The experiment we did was just to see if our communication was reliable enough to have this. If you think about it, what we are doing is we're just doing tournaments repeatedly for the number of points. This is K. We are just doing our tournaments repeatedly. And so this is somewhat demanding in terms of the communication, because just failing one tournament will mean that we have a completely different interpolation. Okay? So what we've done is we have a fixed signal, and we have nodes doing getting the points of the iteration in repeatedly. Okay, so we knew what the result was, and we just measured how many times we would fail to get that result, and we just varied the distance between the nodes from 1.5 to 6x6 grid. We get, as you can see, rather low error ratio, and I think this is a rather demanding application in terms of the communication and what it requires from the reliability of the tournament. About applying our techniques in a multiple broadcast domain, what we've done was basically create single broadcast domains in a multiple broadcast domain. What we've done is we run a clustering algorithm, and this clustering algorithm is basically will color the nodes such that we will have nodes that are partition leaders, and then they can communicate between themselves. They actually form a minimum virtual dominating set. Virtual because we are using a virtual range that enforces that all nodes in this range are in the same broadcast domain. And it's a dominating set because all nodes are either in the set or they are neighbors to the nodes in the dominating set. So we form this clustering algorithm that makes these single broadcast domains. So what you have here drawn is, you see the communication range of this partition leader is this. But we have a virtual range, and we make nodes cluster just inside that virtual range